Good morning, everyone. We are here today to talk about faster CFD post-processing with our TecIO library and FEMixed zones. I am the gentleman on the left, Scott Emley, and my co-presenter is Dr. Dave Taflin on the right. I'll be talking first and he'll be doing the tough stuff later on. So today we'll be talking about the benefits of exporting Tecplot binary files as opposed to ASCII files. FEMixed zone type, it's a new zone type, what it is and why you should use it. New APIs in our TecIO library to export the FEMixed zones and how to use them, and how to export higher order elements in SCPLT files using TecIO. Next slide, please. So the benefits of exporting Tecplot binary files. Well, binary files are faster to write and read than ASCII files. ASCII can be quite slow for large data sets. Tecplot binary files are optimized for Tecplot 360. In particular, the SCPLT file format is smaller for finite element unstructured zone types, including the new FEMixed zone type. TecIO handles the hard part of MPIIO for parallel output. So MPIIO is a MPI library, and we have wrappers around it, so it's a little easier to use. TecIO is free and easy to use. And if you're interested in trying it out, you have a CFD code, Tecplot partner licenses are available for compatibility testing. Next slide, please. What is the FEMixed zone type? Well, it does a couple things. In the past, we used to require that each zone have a single element type in an element shape. So we had only FE brick and FE tetrahedron. And if you had any finite element shapes other than FE tetrahedron, you had to use FE brick, and you would collapse the faces, or you could just write them as separate zones. And if you wrote them as separate zones, you would see boundaries in your volume, like you see on the upper right image if you showed the surface of the zone, the volume zone. So one of the things that FEMixed does is allows you to combine these together into a single zone, and it avoids those boundaries between the element shapes. It also results in smaller files because you don't have duplicate nodes specified in the node map, and it results in faster post-processing for both of those reasons. Next slide, please. It adds support for pyramids and prisms. So we have, previously we just had brick and tetrahedron. We now have prism and pyramid cell types as well. So there's no need to use FE brick with duplicate nodes, like I mentioned before. It results in smaller files and it's faster post-processing. Next slide, please. And the final thing it does, and one of the drivers for adding this new zone type, was to add support for higher order elements. So there's no need to subdivide to linear elements in your code like is often done now, and you get higher fidelity results in post-processing. So we support all those element types you see to the right. That's actually the CGNS designation for the element types, but it's the shape, say quad, underscore, and the number of nodes. Next slide, please. So here's an example. This is a transport aircraft configuration. You can see it has 145 million tetrahedrons, 35 million prisms, and then it has 76,000 pyramids. Those are, in this case, the prisms are near the wall. So you have a triangular mesh on the surface, and then it's extruded out as prisms through the boundary layer. And then you have tetrahedrons in the far field, and those pyramids are just there to kind of glue the prisms to the tetrahedrons as necessary. So in terms of file size, you can see the different options for file type here. With Tecplot ASCII in the table, you can see that using single FE brick zone, which is what you'd either have to do that or have multiple zones. The size of the file is 18.1 gigabytes. Using the Tecplot PLT format, same idea, single FE brick zone, it's 7 gigabytes. Now, if you wrote that out using the SCPLT format, this sizzle file format, it's 3.5 gigabytes, only half as big as the PLT format. We have some, SCPLT has the zones divided up into small subzones, and there's some compression that allows, lossless compression. And then finally, with our new FEMixed zone type, with multiple sections, one for each of the tetrahedron, for all the tetrahedrons, one for the prisms and one for the pyramids, it gets down to 2.5 gigabytes. So you get a substantial savings even over the FE brick zone. This data, by the way, was provided to us by Metacomp. So thank you, Metacomp Technologies. Next slide, please. Now, this also makes for faster post-processing. So this is reading, actually. It's often also faster to write, but the reading, this is basically read and display of this data. With PLT, we don't even show the ASCII because it's quite slow in this case. With PLT, it's 217 seconds. And the maximum RAM is 16.5 gigabytes. With the SCPLT format, it's 76 seconds to read and display this and create this image, and 2 gigabytes of data. It's a lot less data because what we do with this, with sizzle data, is we actually will only load the subzones that are needed to create this image. Well, we need to load the full surface zones. Those are the surface of the geometry, that is. But for the volume, we only need to load the subzones that are around that slice that we're seeing. And so that's a small percentage of the data in the volume zone. So that's why it's so much smaller, 2 gigabytes. With FEMixed zones, it's faster yet, 62 seconds, and it's a little bit larger, 2.8 gigabytes. Next slide, please. So Dr. Dave, I believe this is where you come in.
Yes, thank you, Scott. Now I'd like to talk about the new TecIO APIs and show you some pseudocode to show you where they fit into the overall scheme of calls into our TecIO library to produce SCPLT files, and show you where you can find some new example programs to help you with, specifically with both multi-section output, this FEMixed zone type, and high order element output. So here's the new API for creating an FEMixed zone. And if you've used the TecIO library before, you'll recognize, at least if you've used the new API before, you'll recognize the parameters that are not highlighted. Those, or something very much like them, are used to create every zone type. But the highlighted ones are specific to FEMixed zones, so I'd like to talk about those in detail. The first parameter is num sections. Each element type, the pyramids, prisms, or what have you, needs to be in a separate section. Each section has only one element type. Now, as far as I know, I haven't tried this, but as far as I know, there's nothing preventing you from having two sections that actually have the same element type. I just don't know why you would want to do that. So generally, however many different types of elements you have, that's how many sections you're going to create. The next four parameters are all arrays dimensioned by num sections. And the first one is going to be the cell shape for that section, for each section, pyramid, prism, etc. The second one, grid order, that's going to be just a number indicating first order, which is the classic cell type that we've had forever, or second order, or third order, or fourth order. We support currently up to fourth order for high order elements. The third is the basis function, and if you want to accept, or if you want to use Lagrangian elements in every section, you can just use null or null pointer there, and it'll default to Lagrangian. And at present, that's your only option. However, we are working on implementing serendipity elements as well, which is where you take the full, let's say, 27 nodes for a second order brick element or hexahedral element, and you toss out all of the elements that are in the middle of faces or in the cell center. We don't have serendipity elements yet, but like I say, we're working on it, so expect that in a future release. And the final new parameter is the number of elements. Actually, it's not really new. You've always had to specify the number of elements, but this is per section. So for each section you specify, you have to more or less obviously specify how many elements are in that section. And as always, the return value is 0 for this call if it was successful, and -1 if there was some failure, in which case an error message will be printed to the console. Now, I mentioned the new API. We also have an old API. At least that's my terminology. The old ones, they all started out being just a nice Fortran 66 friendly 6-letter name, TecZNE, TecNod, what have you. They've gotten a little bit longer over time. Fortran 77, I think, allows 24 characters for a routine name. But we've also created this brand new as of a few years ago, API that gives you access to a few features that the old API does not. However, if you're writing PLT files, our older file format, the old API is the only one that allows you to do that. But the new API gives you access to the other variable types that 360 supports. With the old API, you can have any variable type you want as long as it's single or double precision. With the new API, you also have access to integer variable types and can out those to sizzle files. The second API, which is really very similar to one that you'd be familiar with if you've already been outputting parallel partition data, is the API to create a new partition. And that, although it's available in both libraries, you can use that for testing or development purposes if you want with the serial library. Really, its intended use is for MPI parallel output. So you'd be using TecIO MPI, the parallel version of the TecIO library, both of which are installed with 360, but you also get the source, and I'll talk about that later. Now, to the lower left, we've got some pseudocode that just shows you the sequence in which the TecIO APIs are called. And this is for the serial, the non-parallel TecIO library. You'll call TecFileWriter open to open a new file, and you can call this more than once. You can have more than one file open at the same time. And then assuming an unsteady solution for each time step and a multi-zone solution within each time step for each zone within a time step, you'll call this routine TecZone create FEMixed to create each zone. And then for each variable, but with the new API, you don't have to output them in order. But for each variable, you call TecZone bear write float values or double values or int32 values or whatever variable type you have for each variable. You specify all that in the call to TecZone create FEMixed. And for each section, you write the entire node map. And the call to TecFileWriter flush is optional, but if you're writing all of your data to a single file as opposed to separate grid and solution files, and people who do that typically will write one solution file for every time step, so you get potentially a lot of files. But if you're writing everything to one file, an aspect of sizzle output that you should be aware of is that in order to create the subzones that Scott mentioned earlier, we have to cache all of the data your program outputs to the TecIO library. We have to keep that all in RAM. And that, for a long unsteady solution, can use up quite a bit of memory. So for that scenario, we provide this TecFileWriter flush API that directs the TecIO library to do all the subzoning and everything that it needs for all of the zones that you've currently output and flush those to temporary files on disk. And that allows it to clear out all this cached storage and minimize the TecIO library's memory footprint. And then finally, once your solver is completely done, you call TecFileWriter close. And since I mentioned TecFileWriter flush, I'd like to mention another option you have if you're flushing data is to have if you want to have your solver resume later, quit now and resume later, and resume appending to the same file, you can actually have it not call TecFileWriter close when it exits the first time. Then when you launch it again later and it calls TecFileWriter open again with the same file name, it'll detect the presence of those temporary files and resume appending your solution data to them. And keep doing that until you call TecFileWriter close. Finally, I mentioned we have some new examples that show you how to output FEMixed zones, and all three of them happen to output higher order data. And if you look at the title bar there, or just below the title bar, you'll see the path here. This, of course, is on Windows. But for any platform, the TecIO examples can all be found beneath Tecplot's util TecIO examples folder. And I've highlighted the three new ones here. Hexa 27 outputs a second order brick element solution. And Hexa 27 partitioned does the same thing, but it uses domain decomposition to break that each Hexa 27 zone into pieces and output them as a handful of partitions. And you can build and run that one with TecIO MPI and actually have different MPI ranks outputting the different partitions for each zone. And finally, the quad 9 bar 3 shows you 2D and 1D high order element zones. With TecIO MPI, a separate library, we add three new, well, not new, but three additional calls over the serial implementation. For each file, as I said before, you call TecFileWriter open, but immediately thereafter for each of those, you must call TecMPI initialize. Now, I mentioned this is pseudocode. We're not showing any of the parameters here. every API except TecFileWriter close, actually all of them have parameters that you have to pass. But if I put them in here, the slide would get way too cluttered. But once you've called TecMPI initialize, then you proceed as before. But if you're outputting partitioned data, then after you create each zone, you call TecZone map partitions to MPI ranks. This will tell TecIO both how many partitions there are in this zone and which MPI rank is going to output each of the partitions. Typically, you'll have one partition per MPI rank. So you're passing there an array of MPI ranks indicating partition ownership. And then in the course of the solution, for each partition, now I left the time steps out here, by the way, so this is assuming steady state. For each partition, you call this new routine tech FEMixed partition create 32. Looks very much like the other partition routines, but has the parameters specific to FEMixed and HOE data. And then as before, you output your variable data, but for each section now, you call TecZone node map write 32 or write 64 to write each section's node map data. Then again, the optional flush, that works fine in parallel. It doesn't create a bunch of temporary files per MPI rank, by the way. It just creates a handful of files total, and all of the ranks write to those files. And finally, TecFileWriter closed when you're all done. We've mentioned a few times that the FEMixed zone type also gives you access to outputting high order elements up to P4. And we have intentionally used the CGNS winding rules. So you'll know and be familiar perhaps with the order in which nodes need to be output. But there's a link there to look up the CGNS documents that describe this in more detail. Also of note, the grid and your solution data need to be the same order. It is possible to have a lower order grid in general with high order elements than the solution data, but we don't currently support that. And when you output, well, both HOE or any FEMixed, you output one section at a time, and you have to write all of the nodes, the node map for section 1, followed by all the nodes for section 2, and so on, for however many sections you have, and using CGNS as winding order for the node ordering. And this concludes the formal part of our presentation. If you have any questions, please feel free to enter them in your control panel. But I wanted to point out some resources for you. First of all, to get the TecIO source, you can establish or log into your My Tecplot account and then click Product Releases TecIO. If you don't have a My Tecplot account, they are free and we won't spam you. You can optionally sign up for a periodic newsletter, but that's an opt-in, and you won't wind up on anybody's mailing list, we promise, except ours if you request it. The source is free, and if you're doing MPI, you will almost certainly need it because various MPI implementations are not binary compatible with each other. You might get lucky and find that if you're using OpenMPI, find that the version of TecIO MPI that is installed with 360 actually works for you. But it's really a much better idea to download the source and always to build TecIO MPI with whatever MPI compiler you're using to build your solver. Our TecIO source is redistributable, and the only request we make is that if you make any changes, please communicate those to us. We're always interested, as usual, in customer feedback, and any changes that are made will indicate a possible change that we might want to actually make to the library in future distributions. So we'd like to hear about that. Other than that, you're free to redistribute the TecIO in compiled or source form with your software with no strings attached. We have a number of tutorials online and some online training. And finally, if you have any questions in the future, feel free to contact support at the emails listed at the bottom of this slide, and we'll be happy to take your TecIO questions there.